The purpose of this video is to examine fundamentals of stress analysis of built-up beams. By definition, a built-up beam is produced by joining several simple beams. For example, here you can see 4 built-up I-beams where the flanges are welded to the web. I can assure you that this is a built-up beam rather than a monolithic I-beam if you look at this photograph. Clearly, these are huge I-beams for very large structures, and obviously they have to be custom made where metal plates are welded together to form an I-beam, and the key is to examine welds at the base and at the top of the beams. So joints in built-up beams must be sufficiently strong. We certainly do not want the weld or any other joint to undermine the basic loading capacity of a beam. The beams could be formed by gluing, welding, nailing, bolting, etc. And the key feature of stress analysis is that all joints are subjected to shearing. So when we analyze joints, we recognize that shearing of joints has similar features to shearing of simple beams, or stress analysis of joints must be related to shear stress analysis of simple beams. Also, as far as analysis is concerned, all joints can be divided into 3 groups. Point joints, like nails, bolts, screws, line joints, like welds, and area joints, like glue. To motivate our analysis, let us go back to the simplest case of a built-up beam, which involves 2 wooden boards glued together in the middle, so that the total size of the built-up beam is B by H, and in between we have the glue. The stress analysis of this beam is very basic, and we obtain that the maximum shear stress in the entire beam is realized in the glue, and its value is given by this expression. Now what I would like to do, I would like to go back and see how we arrived at this expression so that we can see how we can extend our approach to shear stress analysis in simple beams to analysis of joints. So let me redraw the cross-section of the beam, but now I would like to identify the lower beam as the free body of interest, and of course this free body is produced by cutting through the glue along the plane XZ, or along the horizontal plane of the beam. I would also like to have a side view. So this is YZ plane, this is XY plane. So in this figure, this is the cross section with coordinate x, this is x plus delta x, and of course this is an elementary beam element of length delta x. So if I consider this element, I can show stresses acting on this element. When I cut through the vertical plane at x, I expose the normal stresses, sigma x, and its tension. On this side, the cut is again vertical, and the stress sigma is denoted by x plus delta x. Again, it is tension. And finally, across this plane, there is a shear stress. So this stress diagram could be easily converted into a free body diagram where all stresses are replaced with forces. To this end, let us redraw the cross section. And now I identify the yellow part of the cross section by A star. So that's the area below the cut. That's a familiar A star we've been using all along. And now I will take the stress diagram developed at the previous slide, and I will use it to write down force equilibrium equations. Actually, I need only one equation, sum of the forces on x. It has three terms. The first term is the resultant of the distributed forces, or the resultant of sigma x, and sigma x is distributed over the area A star, and therefore here we have A star. The center integral is the same, but for the normal stresses operating on this plane, so it's still the same A star, but now the stresses refer to this section rather than to this one. And finally, I calculate the force induced by tau by multiplying tau by the area. This area on this side is delta x. On this side, it's b. So the area is b times delta x, and that's the equation. It is useful to rewrite this equation using another view. So first, let me copy the cross section. And now, instead of showing the view in the xy plane or the side view, I will show a three-dimensional view. Okay. So on this element, x-axis is perpendicular to the plane. This face is exactly this face. This tau operates on the plane covered with the glue. And here, instead of showing the normal stress distribution, I show the resultants induced by the stress sigma of x and the stress sigma of x plus delta x. Of course, this is another view of the free body diagram, and the equilibrium equation does not change. Maybe it just simply helps you to understand where different terms are coming from. Let me continue with the equilibrium equation, and first I'll rewrite what I had on the previous slide. And now I also recall that sigma is equal to my over Iz. So now I can put these two guys together, and I modify the first two terms in this equation. The last term remains the same. All I did, I substituted this expression into the integrals, and therefore this form transforms into this one. Now I can collect the terms and observe that as far as the area integration is concerned, IZ is a constant and M's do not depend on the coordinates within the cross section. They depend only on X. Therefore, M's and IZ can be taken out and we can rearrange this equation in this form. Please take your time to see how things are done, but now this is the form that allows us to arrive at this equation. First, we observe that this term is the derivative of m, or the shear force. The second term is the first moment of A star with respect to the z-axis, and we denoted it by q. And finally, the last term simply migrates to the denominator of this expression. And that's the basic expression that we derived for analyzing shear stresses in simple beams. Now, let me observe one interesting feature of this equation that will be very useful for analyzing the joints. So first I'll rewrite this equation. And now I observe the following, that this is the resultant force of the normal stresses on the cross-section X. This is X plus delta X. And this basically the shear force needed to balance these two terms. And to recognize this, I'll just rewrite the last term as delta F. So that's the shear force that the joints must produce in order to balance the free body diagram. Now, I can keep delta F as the primary variable and solve this equation for delta F. Okay, so you can see the difference of the moments, Q and IZ. And now I would like to introduce the shear flow. The shear flow, by definition, is the shear force in the joint per unit length, delta F, delta X. And of course, by bringing delta X, I can rewrite this difference as the derivative of M, which gives me VQ over IZ. So by introducing the shear flow and the equation for the shear flow, I will be able to analyze a wide class of problems involving joints.